with probability 100%, you will see a question like that on the exams that you take. So if I think it would be a good idea to make sure that if we're seeing new symbols, we're making sure that we've done the work to understand what those things mean. Even if it means like making flashcards or coming up with like our own like glossary of terms, I think that that would be a really good exercise as a student to make sure that as we're learning new things and seeing new things, we're integrating them into our knowledge bank so that we can make use of them later. So thank y'all for that. Hopefully that one went okay. And as always, if we have questions about anything, feel free to let me know. Ideally sooner rather than later, because I like teaching. I try my best to do a good job of that. And I'm here to help, but also the sooner if you need help, the sooner that you ask for help, the sooner that that help can be provided. So that's the end of my soapbox, and we can get on to the lesson for today. Today, we are going to talk about developing the one group diffusion equation. So like up until this point, we have seen a bunch of new, or at least we've seen a bunch of terms, we've seen a bunch of quantities and equations, and we want to start using those things that we've learned up to this point to start obtaining neutron distributions. Um, to understand what a reactor is doing, we need to be able to know how are neutrons being produced, how are neutrons being lost. So that means that we need to know the different kinds of reaction rates that are occurring in our reactor. And then if we can piece those things together, we can do that with a conservation statement that will allow us to, that'll be our starting point from which we can start figuring out what kind of neutron distributions we have in a given context. So when we talk about like a conservation equation, do y'all remember like the general, like in words, how we would describe the like equation for a conservation statement? Okay, so like that's an example of conservation of energy, and that is like a conservation statement. You've got your ins, you've got your outs, and then you've got a zero, which for energy, energy is conserved. So the ends equal the outs usually, unless you have external forces acting on your system. And so conservation of energy is a good way to think about it. And we can talk about conservation even in a more general sense. If we're talking about conserving a neutron population, then what we would say is that we have the rate of change of our population of interest. So in this case, the rate of change of the neutron population is what we have on the left. And the way that the population of neutrons can change, just like the way that the population of anything can change, is if you have rates of gain of that quantity, those are going to add to the population. And if you have things that are taking that quantity away, those would be the losses of that quantity. So the change rate of this population is going to be the gain rates of my neutrons, of my neutron population. And then I subtract all of my loss rates of that population, loss rates of the neutron population. And the gains and losses are a sum in that you could have multiple gain rates, you could have multiple loss rates, and you're just adding all of those things. All of your gain rates are positive in the equation, all of your loss rates are negative. And so if we can develop equations for the rate of change of our population, for the different gain rates and the different loss rates, then we can develop a mathematical equation that we could then solve that would tell us about our neutron distribution. So it's a very simple kind of idea, but it's also very important. This equation right here can take you very far in lots of different contexts too, like conservation of energy is a form of conservation statement. When you do fluids, you do conservation of mass. momentum, and energy. Those are also conservation statements. And so for any given setting, you're going to find that there's only one distribution that will satisfy that equation in complete detail, at least for any different context or any different kind of reactor. So we want to have this equation kind of in the back of our mind, and then we're going to start using it to piece together and solving or figuring out the distribution for different contexts. So the simplest context that we could talk about would be an infinite reactor. So an infinite uniform medium, like maybe it's an infinite block of uranium-235 or an infinite block of some kind of material that could fission, like a multiplying medium. Um, we're going to assume that in that medium, all the neutrons have the same speed so that we're not dealing with like an energy distribution of the neutrons. We're going to assume that the cross sections for the material in that medium have been properly averaged over the range of nucleus motion in that medium. And then we're going to assume that we're putting neutrons into this infinite medium in a way that's uniform so that in any location in that medium, the neutron density is basically the same at every point. And we're also going to assume that those neutrons are isotropic and that they don't have any preferred direction. The kind of neutron population looks the same no matter where you go. And then that's the simplest context that we could talk about for like a nuclear reactor. And we want to ask the question and figure out how that population would evolve with time. And so we want to use we want to figure that out, and the way that we would do that is with conservation. We would write this conservation statement that says just like what we had wrote before, that the change of my population, the rate of change, equals all of the rates of gains minus all of the rates of losses. So in words, we could say that the change rate of our neutrons equals the ways that neutrons are gained in this problem and the ways that neutrons are lost in this problem. So in this problem, how could we gain neutrons? Like what mechanism by which could neutrons be added to the infinite reactor? Fission, right? So we're going to have a fission rate, the fission rate. And that's going to be our only gain mechanism if it's an infinite medium. And that fission rate is going to have units of fissions per second. So we need a multiplier up front that talks about how many neutrons we get per fission. And we use the symbol nu, which kind of looks like a V, but it's a little curvy. And nu sub F is what represents the average number of neutrons that come out per fission event. So if you multiply those two together, that's like my production rate of neutrons. It has units of neutrons per second. If if I can fission to produce neutrons, how could I lose neutrons in this infinite medium setting? Like if it's all uranium-235, if a neutron interacts with uranium-235, does it fission every time? There's absorption, right? Sometimes we get absorbed and we don't cause a fission. So any absorption would technically be a loss. And some of those absorptions would lead to gains because that absorption would cause a fission. But some of those absorptions would just be like radiative capture or some other reaction that doesn't cause new neutrons to be born. So the rate of loss is just going to be my absorption rate. Perfect. So that's what our context looks like for an infinite medium. My only gains are due to fission. My only losses are due to absorption. Um, how come we didn't talk about leakage in this context? How come we don't have leakage in our conservation equation?
Well, it can't leak at the same.
Perfect. There's no leakage from an infinite medium. Awesome. So we have this conservation statement, and now what we want to do is turn this conservation statement in words into a mathematical expression. And that's what we are going to do next. So if we look at, it's an infinite medium, if we look at some little volume of that medium, um, we might ask the question, is there going to be any leakage out of that? If we look at this infinite medium that's a uniform, and then we look at some little subvolume of that medium, would we have any leakage out of that volume? It's kind of a trick question in that there could be leakage out, but there could also be flows in. And if the medium is uniform, then whatever rates in you have of leakage are going to be balanced by the rates out of leakage if it's uniform and isotropic. So in this case, no, because everything is uniform. So our ins equal our outs. Whatever leaks in is just going to leak out if it's an infinite uniform medium. So that means that the conservation statement that we just wrote for the infinite medium also holds for every subvolume in the infinite medium. And that means that essentially our medium is going to be uniform, and that means that our flux isn't really going to have any position, or our neutron density isn't going to have any position dependence. So in our equation, we have the change rate, we have the fission rate, and we have the absorption rate that we need equations for. We already talked about how reaction rates come from the scalar flux. And we also talked about that we can talk about the scalar flux in terms of the neutron density and the neutron speed. And if I want to get the scalar flux in terms of these two quantities, the density of neutrons and the speed of neutrons, what do I do with those two terms? How do I write the scalar flux in terms of the density and the speed? Perfect. Yeah, they're just multiplied together. If I do n times v, the neutron density times the neutron speed is the scalar flux, and I think we showed that last time. So that's definitely, if we didn't remember that, that's a really good thing to remember, how we can write the flux in terms of the density and the speed. So I'm going to talk about those quantities that we need equations for, and I'm just going to break them down term by term. So our change rate is going to look like d by dt, because it's a rate of change of the quantity that we're keeping track of. And in this case, we're keeping track of the number of neutrons. So to get the number of neutrons, I'm going to take that neutron density little n, and I'm going to multiply by the volume, the sub the sub volume, or the volume of our little sub volume that we're looking at. Um, and then so that's how I could write the rate of change of the neutron population in this context. And the neutron density could change with time, but this little volume is a fixed volume, so it doesn't depend on time. And that means that this volume can actually come out of the derivative. So I could write this as volume times dn dt. So that's my change rate. And then I need my fission rate. Um, the fission rate in this context is just going to be my fission rate density. So like my number of fissions per unit volume per unit time. And then to make it a fission rate, I'm going to take that density and I'm going to multiply by that volume V. Um, so it's fission rate density times the volume. And then the fission rate density is going to be my macroscopic cross-section sigma f times the scalar flux. That's my fission rate density. And then I'm going to multiply by that volume V to turn that density into a rate. And then that's just the fission rate. Technically, that new F is still going to be in front of it once we plug all of these into our conservation statement. And since technically we are trying to get an equation for the neutron density, we're trying to say how the neutron population evolves with time, we can write that flux in terms of the density, right? If by just substituting in n times v here. So this is also the same thing as sigma f times nv times that big volume v. So that's my fission rate in terms of the neutron density. And then I need the absorption rate. And the absorption rate is going to look very similar. I'm just going to have my absorption rate density times that volume. And then the absorption rate density looks just like the fission rate density, except I use a sigma A instead of a sigma F. So I could say sigma A times phi times that volume. And then again, I could write that flux in terms of the density times the speed. So that would be sigma A times my numbered neutron density times the speed times that big volume. So this is where I was talking about needing to know the individual terms so that we know how to put those things together to compute more complicated things like reaction rates. And so these are the mathematical expressions that we can plug into this equation to then have an equation that's mathematical and that we could start to solve. So that's what we're going to do. We're going to plug all of these definitions into our conservation statement. So we're going to just kind of rewriting, we're going to have V times dn dt equals, this should be a new F. So I'm going to have new F times that fission rate, which we said was sigma F times N times the little v times the big V for volume. And then minus the absorption rate, which was sigma A times little n times little v times big V for volume. So now, instead of having an equation in words, we actually have a mathematical expression, and we can hopefully solve this if we're lucky. And in this case, the volume appears on every term in our equation, so that volume is actually just going to cancel out. If we divide both sides by the volume, then that volume is just going to cancel. And then notice how on the right side, both of these quantities, both of these terms contain the product NV. So if we look at that equation, we could factor the NV out. And that means that on the left, we have dn dt. And then if we factor the NV out, then what we're going to have left is nu F times sigma F minus sigma A. And then all of that is times little n and little v. This right here, we've just developed a differential equation that will describe our neutron population and how it evolves with time. And now what these quantities look like are a change rate density. If I think about the units of every term in this equation is going to have units of neutrons per unit volume per unit time. So instead of this being a balance of the rate, it's become a balance of the rate densities. This first term would be our change rate density of the neutron population. This second term would be the fission rate density of our neutron population. And this third term would be the absorption rate density of our population. And this differential equation might look complicated, but it's actually just like, it's basically like dy dt equals a constant times y, right? All of this stuff in front of the quantity n is the like variable that we're solving for, and all of this stuff that's being multiplied by the neutron density is just a constant. So this equation almost looks just like our favorite differential equation that we know and love, that we've solved so many times, and we know that if we were to solve this equation with an initial condition, then we would get something that looks like this. And that's what we saw for the intensity equation. That's what you would see for radioactive decay. This equation comes up a lot in nuclear engineering. It's going to look like an exponential. And so I think that that is just the coolest thing ever, that we can take just a simple conservation statement, we can break out the terms of that conservation statement, and then we can get a mathematical expression that can tell us something cool and interesting and informative about what that population is doing. In this case, how that population would evolve with time. So we just determined this. It shows that in this context, our neutron population can evolve exponentially. And if it's an exponential, then the behavior of that exponential is going to depend on the sign, the SIGN, inside of that exponential. So depending on if these constants in here are positive or negative or zero, that's going to influence if we increase exponentially, decrease exponentially, or if we remain steady. And these quantities right here are the only quantities that can actually influence the sign of the inside of the exponential. My nu f, my sigma f, and my sigma a. And so that time evolution is just dictated by those terms. And what kind of properties are those? The nus and the sigmas, what kind of properties would we describe those as? Like if this was a reactor of uranium versus a reactor of made of graphite, then those quantities would be different, right? Like every material is going to have a different sigma, every material is going to have a different nu. So these are just simply material properties. This population is going to be dictated, the time dependence of this population is going to be dictated only by material properties. And those are things that we could look up. We could go onto Janus or any other nuclear database and we could find what those quantities are for our material. So these material properties are going to influence what our population does with time. And we want to think about how does the nu F sigma F and the sigma A need to compare if we want our population to grow exponentially, be steady, or fall exponentially. So if our population grows exponentially, this quantity needs to be positive. And for this quantity to be positive, it means that nu F sigma F has to be greater than sigma A, right? Like if nu F sigma F is 10 and sigma A is 5, then we got a positive 5 here, and then we've got a positive exponential. So with time, the neutron population would increase exponentially. For it to be steady, it means that we have e to the 0. E to the 0 wouldn't change with time because e to the 0 is 1. And it would be steady if nu f sigma f was exactly equal to sigma a. So it would be steady if nu f sigma f was equal to sigma a. And then it would decrease exponentially if sigma a was greater than nu f sigma f. So if nu f sigma f is less than sigma a, then our population decreases exponentially. And that kind of intuitively, hopefully, makes sense that if we have effectively a larger fission rate than an absorption rate, then we're going to end up increasing the number of neutrons in our medium as time goes by. If these are perfectly in balance, then that population isn't going to change. And if we have a larger absorption rate than our fission rate, than our production rate, then the population of neutrons is going to decrease with time. So if these are like our production and loss mechanisms for this infinite reactor, we could talk about what the infinite multiplication factor would be. We talked about the multiplication factor last time, and I think the most simple way to think about it is that it's going to be my production rate divided by my loss rate. Any configuration, you can think about the multiplication factor as just the ratio of production to losses. And in this case, I only have one way that I can produce neutrons, which is by fission. So my production rate was that nu F sigma F times the flux times the volume. And my loss rate was just sigma A times the flux times the volume. And so notice that in this definition, the flux and the volume are the same on the top and the bottom, so they cancel. And that gives us our expression for the infinite multiplication factor, which is nu F sigma F over sigma A. So we've probably seen that equation before. I feel like it's a good point to just remind ourselves that we have the tools to predict these kinds of things. And in that case, for the infinite medium, that's what our multiplication factor would be. And this kind of leads us to the same kind of conclusion here in that if k is 1, then nu f sigma f and sigma a are balanced. If k is greater than 1, we're supercritical, and that means that our nu f sigma f is greater than sigma a. And if we're subcritical, that means that sigma a is going to be greater than nu f sigma f. So that's the infinite medium problem. That's like the simplest configuration that we could talk about. And on the homework or it says homework here, it's just the problem sets because they're not graded. There's an example that talks about that infinite medium problem, but then adding in a fixed source. So like in reactors, when we're starting them up, sometimes they'll put a neutron source in the reactor to kind of kick the chain reaction off. And californium 252 is a very common neutron source because it has a decent chance of doing spontaneous fission. So californium-252 is cool because it just like kind of spontaneously decays and emits neutrons. Um, so if we had this extra source term in our equation, then we would have an extra gain mechanism because of that source producing neutrons into the medium. And if we were to write our differential equation, including that source term, we would have something that looks like this. It's going to look basically just like what we had before, nu f sigma f minus sigma a times nv, but then we're going to have a extra gain term, which would be representing that external source. And each of these quantities in this equation still has units of neutrons per unit volume per unit time, so the units in my equation are consistent. And if you wanted to start from the very beginning, we would get to the same point. It just in your gains, you would have the external source times that volume to make it a like source rate instead of a source rate density. But then that volume would have canceled out in every term, and you would have ended up at this same spot. This equation is a little bit harder to solve because it's no longer a separable equation. That the previous equation that we saw, everything was just being multiplied together, so we can move the n term to the other side, we can move the dt term to the other side, we can integrate both sides to get our result. Now it's not separable because we have this extra term being added to the differential equation. You can still solve this one. It's just a little bit more involved because you have to use like integrating factors. So this equation was given kind of as a starting point for one of those homework problems. And I think that was the only thing that's on the first problem set that we hadn't talked about yet. So that's kind of giving you the starting point for that last question on the problem set that you might have been confused about. So yeah, if we want to get past the infinite medium problem, then we need to start talking about if we have like a finite reactor, then finite reactors are going to have leakage. Real reactors, neutrons leak out, and so that has to be accounted for in our conservation equations. Um, we use that flux to compute reaction rates. There's another similar quantity that we use to compute leakage rates across the surfaces where those neutrons are escaping from. And that quantity, we use a symbol big J for that quantity. And big J has a name. It's called the net current density. Big J, it's a vector, so that's a little hat. And this is the net current density. Um, it has the same units as like an intensity. So like neutrons per unit area per unit time. And so it's kind of confusing because you could think of it as having the same units as the flux, but it doesn't have the same physical meaning because J tells you about a leakage rate through a surface. It's basically the number of neutrons per unit area per unit time that are escaping through that surface, whereas the scalar flux is can sometimes be thought of in a similar way, but there's no directional component to the flux, whereas there is a directional component to the current. And the way that I get leakage rates out of the current is I take that net current density and I multiply it by a unit vector that's pointing outward from my surface. So if E hat n is the outer surface normal vector, and I multiply those two together, then that's going to give me a leakage rate. It's going to that quantity is going to basically describe the leakage rate across that surface. So or you could think of it as the areal rate density at which neutrons are passing through that surface. And if we want to turn this areal rate density into a leakage rate, then we just have to take that quantity and then integrate it over the surface over which those neutrons are leaking out. So the net leakage rate is going to be a surface integral of J, and J would be evaluated at the external surface, and we're going to multiply it or dot it with the E hat normal at that external surface. And then that we're integrating over the area of the surface. So I'll say DAS. That's like the expression of the surface integral that we would use to compute leakage rates out of the surface if we knew what the current was at our surface. So like just like to draw a little picture that might help illustrate this a little bit. If I had like a lima bean shaped reactor and I have some coordinates x, z, and y, at some arbitrary location on this surface, we would have a little surface element, and that surface element would have area dAs. That surface element is going to have an outward unit normal, which is our E hat normal vector evaluated at that external surface. And so, like in terms of that position argument, what we're saying is that this point right here in my coordinate system, that point is the R external. It's just wherever on that surface where we like some coordinate where the surface is, and then that e hat n is the unit vector that's pointing out of there. And so that j might not be perpendicular to the surface. It might be in some weird angle to the surface, but when I dot them together, I get the component of j that's just leaving that surface perpendicular to the normal. And then if I integrate that over the entire surface, then that's what gives me the net leakage rate through that surface. And now that we have an expression for leakage rate, then we could talk about doing conservation on a reactor that has leakage, because now we have a mathematical expression to talk about what that leakage rate is. So we're going to kind of extend that simple problem. A lot of the stuff is going to be the same. We're going to assume a uniform medium, so no variations in our material properties. We're going to assume one group, so all of the neutrons have like the same average speed. We're going to assume properly averaged cross sections. We're going to assume no sources, but we're still going to allow for there to be fission within the medium. And now the reactor is finite, but it's surrounded by a vacuum. So that means that we have leakage. If it's a finite reactor, then we can have leakage. So the gains in this case, we're still going to have gains due to fission. But now we're going to have an extra gain term because of neutrons leaking into our volume. So we have an in leakage term. And then the loss from before is still the same, that we could still have absorption. But now we could also lose neutrons if they leaked out. So I'll call the neutrons leaking out our out leakage. So if we're thinking about change rate equals gain rates minus loss rates, these are going to be the components of our gains. These are going to be the components of our losses. And from there, we can kind of do just like what we did before. We can start developing equations for these individual terms, and we can plug them into our conservation statement. So in this case, this is what that conservation statement is going to look like. Anything that's a gain is a positive term. Anything that's a loss is a negative term. And so if I just start with the left-hand side and develop equations for these individual terms, it's going to look a little bit different now because our medium, if our medium is not infinite, then the flux can vary with position. And that means that we can't just, in the sense that we're looking at a subvolume, instead of the subvolume being a volume V, it's a differential volume. And then if I can find out what's happening in that differential volume, then I add all of those up by integrating over the volume to get the accumulative quantities for like the population gain, the change of my population, the production rate, and the loss rates. So in this case, I'm gonna have, for example, for my rate of change term, I'm gonna have d by dt of my neutron density times that little volume dv. And I'm going to be integrating this over the entire volume of the reactor. The inside would tell me what's my rate of change in some little volume dV. And if I were to integrate that over the entire volume, that would tell me how the change of that of my population in the entire reactor is changing with time. And if I use the fact that phi equals NV, where little v is the neutron speed, then I can rewrite this equation in terms of the flux instead of in terms of the neutron density. So that means I'm gonna have a volume integral. Oh, also the dV doesn't change with time, so the dV can come out of the differential. So I'm gonna substitute in, which would be 1 over V. Um, Here, let me stop skipping steps. So I'm gonna have d by dt of 1 over V times N times dV. Just plugging in, sorry, this should be flux. Substituting in this definition for n, which would be flux over the velocity or over the speed. And then I can start thinking about what of these quantities would be pulled out of the differential. And so this speed isn't going to change with time because we're assuming one speed. And then the differential volume can also come out of the time operator. So this term is going to look like a volume integral of 1 over V times d phi dt, and then also times a dv. Hopefully that makes sense, even though I kind of might have confused us a little bit. The 1 over v comes out of the differential with respect to time. The differential volume also comes out of the differential. So all that's left inside of the time derivative is phi. So I have d phi dt, I have a 1 over v factor, and I have the differential volume factor. And it's a similar story with the production rate. I'm going to have that production rate density, but then I'm going to integrate it over the volume to get the total production rate. So I'm going to integrate over the volume of my production rate density, which, sorry, I need my nu here as well. So it would be nu F times sigma F times phi times that differential volume. That's my production rate density integrated over the volume to just give me my production rate. And my absorption rate is going to look very similar. I'm going to integrate my absorption rate density over the volume. And my absorption rate density was just sigma A times phi. So I've got my rate of change, I've got my production rate, and I've got my absorption rate. And the other two things here, I've got in leakage and I've got out leakage. And I've written it like this to see that I have in leakage minus out leakage. And my ins minus my outs would be the negative of my net leakage. So effectively, if I look at those two terms together, that's the negative of my net leakage rate. And we had just said that that net leakage rate, I'll say L net, is that surface integral of J evaluated at that surface, dotted with that outward surface normal, and then it's an integral over the surface dAs. At this point, we have expressions for every term, but there's a little issue, which is that everything else in our equation, the first three quantities are volume integrals, whereas this fourth quantity is a surface integral. So if we could clean this up a little bit, it would help our problem solving a lot. And if we recall from calculus, our calculus studies, we have a powerful equation that allows us to convert a surface integral into a volume integral, and that's by using the Gauss divergence theorem. So if we recall the Gauss divergence divergence theorem, then we can write this as an equivalent volume integral. And that equivalent volume integral would be the integral over the volume just of J, sorry, of the divergence of J. and then that's integrated now over volume. So we're making clever use of Gauss's divergence theorem to rewrite the net leakage from a surface integral to a volume integral, and that's going to allow us to move further in our problem because now every term is a volume integral. So if every term is a volume integral and I have some volume integral on the left-hand side equals another volume integral on the right-hand side, if I have two integrals over the same quantity that are equal, that means the function that I'm integrating or whatever's inside of that integral has to be the same. So if I put everything together, it would look like this. And if I kind of think about what I have on the right-hand side, all of these terms are inside of the same volume integral. So this function on the inside of this volume integral equals this other function on the other side. And that means that the volume integrals are equivalent, so their insides are equivalent. So now I have a differential equation that has been simplified, and I've gotten rid of all of my integrals, which is nice. That means I'm closer to solving the problem, but I still have an issue, which is the number of unknown variables. If y'all are looking at this middle equation here, how many unknown variables do we have at this point? Yeah, and so the technically it's just two. But we said both of them. It's the flux and it's the current. This is just an operator. The divergence operator is basically just saying like mathematically it's telling you to take some derivatives of that quantity. So fundamentally, but I have two unknowns, which is a problem because I only have one equation. So if I want to move forward, I need some way to close the equation. And to do that, I'm going to make an approximation. You can make lots of approximations, but some of them are better than others. In this case, I think the best approximation to make is that we can say that that net current J is approximately equal to minus D times the gradient of our flux phi. And this is using something called Fick's law. And Fick's law comes from the study of gases. Um, and this picture is kind of illustrating it. So like imagine that I had a pizza and I got my pizza box and I put it over here and then I opened the box. So what at the beginning, y'all over there in the back wouldn't smell the pizza box. You wouldn't smell those pizza particles at first, but over time, those pizza particles would diffuse through the room. And so like this kind of corner is where my pizza box started. And over time, those pizza particles are going to diffuse through the room where y'all would smell them first, y'all would smell them later, and way in the back, y'all would smell them last. So that's where this idea comes from. We're basically saying that this current of my neutrons is going to look similar to a gas where so this arrow is pointing in the direction that those particles are flowing, right? They're going to be flowing from the high concentration side to the low concentration side. So this arrow represents J, which is the direction of particle motion, the direction of particle motion. And Fick's law says that that direction of particle motion is in the opposite direction to my gradient of the flux. In other words, it's in the opposite direction to the concentration gradient. So if the concentration gradient is the gradient of the flux, we're saying that it's moving in the opposite direction of highest concentration. So that's what Fick's law says. It says that my current moves opposite to my concentration gradient. And D is called the diffusion coefficient. It physically has units of centimeters, but it doesn't really have physical meaning. The diffusion coefficient is kind of just like a proportionality constant that makes this equation, makes the units of the equation make sense. And what you do for that diffusion equation depends on where you're at in your studies. Right now, we're just going to approximate that diffusion coefficient as being 1 over 3 times the total cross section. And this is a result that comes from neutron transport theory. We don't have to know neutron transport theory to do nuclear engineering 304, but in diffusion studies, we kind of borrow from transport theory in some places to make the math more physically realistic. Um, so this is just an approximation. It's not an exact law, but it's pretty good for large homogeneous reactors where you don't have a lot of absorption. So if we make that assumption and we substitute that into this equation, then we arrive at the one group diffusion equation. So this right here is what we would end up with once we substitute Fick's law into our the equation that we have. So we've got four terms. So like each of these is a term. This would be term one, this would be term two, this would be term three, and this would be term four. So we have four terms. Each of these terms in the equation has to have the same units for the equation to be dimensionally homogeneous. And so we want to think about what the units of each of these terms are. So if I think about like this first one, I've got 1 over v. What would be the units of the reciprocal of speed? Perfect, right? It's just the opposite. If speed is meters per second, the reciprocal is seconds per centimeter. And then d phi dt means like the change in my flux divided by my change in time. So if I think about what my flux units are in the numerator, and my flux has units of neutron centimeters per centimeter cubed per time. It's a neutron path length rate per unit volume. So that's like the units that I would have in the top of that differential, and it's d phi dt, change in my flux over my change in time, and that over my change in time is going to give me units of 1 over seconds. So this is like the units of my d phi term. These are like the kind of units of my 1 over dt term, and these are the units of my 1 over v term. And so if I think about how those units simplify, these seconds up here can cancel these seconds over here, and these centimeters right here can cancel these centimeters right here. So ultimately, what I'm left with in terms of the units is neutrons per unit volume per unit time. So this quantity has units of neutrons per unit volume per unit time, and it contains a time derivative of my neutron flux. So this quantity physically is going to represent the rate of change because it's got a time derivative. It's the rate of change of my neutron density. That's the quantity that says how my density changes with time. Um, and yeah, it has units that agree with that. It's got neutrons per unit volume per unit time. That second term, I've got a diffuse. So if I look at my second term, I've got a diffusion coefficient, which has units of centimeters. And then I've got this del squared is the Laplacian. Um, when I do the gradient or when I do the divergence, it means I'm taking first derivatives, and then I am technically doing the divergence of the gradient, which gives me that Laplacian. And so when I do the divergence of the gradient, I end up taking second derivatives with respect to space. So the Laplacian term effectively has units of 1 over centimeters squared. It's kind of like I'm taking the spatial derivative twice. So I have a d by dx and then another d by dx if it's like a 1D problem. And then the flux has normal flux units of neutron path length per unit volume and per unit time. And so if I think about the units here, then these let's see, how do I want to do this? So if I make these centimeters here cancel 1 centimeter here, And then I make these centimeters in the denominator cancel these centimeters in the numerator, then notice that this quantity, as we hopefully expect, also has units of like a neutron per unit volume per unit time. And this quantity has that Laplacian in it, which came from my net leakage term. So this is a quantity that tells me about my net leakage, but it has units of neutrons per unit volume per unit time. So the way we would talk about this physically is that this is my net leakage rate density. It's the net leakage rate density. It's the density of neutrons per unit time that are leaking out of my reactor. That third term, where's my pencil? That third term, I've got a new F, which is the number of neutrons per fission. I've got a sigma F, which is the number of fissions per neutron distance traveled. And then I've got my flux, which has units of neutron path length per unit volume and per unit time. So if I think about my units, then fissions cancel fissions, neutron path length cancels neutron path length, and what I ultimately have is a quantity with units of neutrons per unit volume per unit time. So in this case, it's got a neutron density rate for units, and it is related to nu F and sigma F, which was my fission production. So physically, what this quantity represents, I can call this my production rate density. My production rate density is the number of neutrons per unit volume per unit time being produced by fission. And then my very last term is just a sigma A times the flux. And so that sigma A has units of absorptions per unit neutron distance traveled. The flux has units of neutron path length per unit volume per unit time. And then we kind of have like an invisible factor of one, which says just that for every absorption that happens, I lose a neutron per absorption. So these absorptions cancel these. The neutron path lengths cancel the neutron path lengths. And look at that. I've got units of neutrons per unit volume per unit time. And so physically what this guy represents, because it has those units and it has to do with a absorption, this is what I would call my absorption rate density. This is the absorption rate density. Number of neutrons per unit volume per unit time that are being absorbed. So this right here makes up my one group diffusion equation. That's what this equation is. This is going to be a very powerful and like useful model for us to understand. We're going to use this equation to understand all kinds of things about how neutrons spatially distribute themselves in various reactor geometries. It's not exact because we made that Fick's law approximation, but not all models are correct, but some of them are useful, and this is a very useful model. If we think about now it's just got one unknown, right? The only unknown is the scalar flux. And technically, this scalar flux is it's gonna be a function of time if we have a time derivative here. And the Laplacian is basically saying take second derivatives with respect to space. So if I think about what kind of differential equation this is, because my solution can depend on position and time, this is no longer an ordinary differential equation. This is a partial differential equation because we have space and time derivatives in the equation. This PDE, is this PDE linear or nonlinear? When we talk about linear, we're talking about the um We're talking about in our equation, the variable that we're solving for is the flux, right? And so if we're asking if it's linear or nonlinear, we're just asking, does the variable that we're looking for contain powers other than one? If the power on my variable is one, then it's a linear differential equation. If the power on my variable of interest is something else, then it would be nonlinear. In this case, we only see flux to the power one, so this would be a linear differential equation. And then we can talk about the order of the differential equation, both in terms of space and in terms of time. In terms of space, the order of this differential equation would be second order because that Laplacian has to do with second derivatives spatially. But then in terms of time, it's first order because I only have a first derivative of time in my equation. So this diffusion, this our one group diffusion equation is a partial differential equation. If we're lucky, we can still solve it, and that's what we're going to end up doing for like the rest of. Well, we're going to talk more about the equation today, and then we're going to spend all of next class doing examples of deriving results from this equation. So I think the next thing I wanted to talk about is just some general partial differential equation stuff. In general, if you have a partial differential equation, the equation itself is only valid within the domain of the solution and not at the boundaries. If I want to know what happens at the boundary, then I need boundary conditions. And so once I get the solution to this equation, it will satisfy both the equation, it'll satisfy the domain and the boundaries. And so if I want to obtain a solution to this equation, I have to apply my boundary conditions. And that means that basically for a PDE, the physical boundary conditions have to talk about my solution variable at every point along the boundary and at all times t. So there's different ways that the boundary condition could be provided. You could be given a boundary condition that just says the value of the flux. That's called a Dirichlet boundary condition, and that would mean that we're being provided the flux at every position on the boundary and at every time t. This R external is just notation to say this is the point along my boundary. And I need to know what that flux is along my boundary at every position along that boundary and at every time t. You could also be told about the component of the current that's normal to that boundary surface. And so that means that I would be taking my outward unit normal of that surface. For it to be normal to the surface, I have to take that outward normal and I have to dot it with the current. And the current is going to be based on the gradient of my flux because of Fick's law. So this is going to be Rext and time. That's the other way that these boundary conditions could be given to you is in terms of the normal component of the current at that boundary. Um, for right now, we have a vacuum boundary condition. So uh, we're not going to need the normal component boundary condition right now. But when we start doing multi-region reactors, where we have like one material next to another material, the way that we merge the solutions from one region to another is by that kind of boundary condition. It's like an interface condition. And then you can also have and that's called a Newman boundary condition in terms of like the mathematical way that that type is described. And then Robin boundary is a combination of the two, where you're given some combination of the flux at that surface and at all times t and this guy. For the case that we currently have, we're saying that it's a bare reactor. So that means that like I've got this reactor itself, but then outside of the reactor domain is vacuum. So if I have a vacuum boundary condition, what does that mean about the flux at that surface, at that outer surface, and at all times t? What does that flux have to be if I have a vacuum boundary condition? Do we know what we mean when we say vacuum? Like if we're out in outer space, they would refer to that as like the vacuum of space. And if we're in outer space, there's no air, there's no particles, mostly. So for a vacuum boundary condition, it means that the value of my flux is zero. I've got no particles there. So that's the kind of boundary condition that we have right now. It's like the nicest and the simplest kind of boundary condition we could have. As we go later, we'll deal with more boundary conditions, but for right now, we just got a vacuum boundary condition, which means that the flux at that outer surface is zero. This deals with boundary conditions, which kind of says what I need spatially to satisfy that original differential equation. The other kinds of conditions that I need have to tell about how my population changes with time. So I need like an initial condition in terms of what's happening with time. So because the PDE has a first order time derivative, I need to specify just one initial condition that says what my solution variable looks like at time zero. So notationally, we would say that that initial condition is going to say my flux everywhere in my reactor, and at time zero, the initial time is just a constant that might it's a constant in time. We basically need to apply, we're specifying the shape of my function, the shape of my flux at the initial time. And so that's what our initial condition would look like. And whenever we think about like the definition of a scalar flux as a path length rate per unit volume, because the scalar flux is a physical quantity, it has continuity conditions and what we call physical realizability conditions that give us it kind of constrains what kind of function our flux could have. So for continuity, the flux has to be a continuous function within the reactor volume. When we talk about continuity, the flux has to be continuous within the reactor volume. That means that if I go from the center of my reactor to the outside of my reactor, that flux has to be a nice smooth function. It can't have discontinuities within the volume itself. And then when I think about physical realizability, it just tells us what kind of solutions we could ignore for a flux. So, for example, if a flux has to do with a path length, it can never be negative because there's no such thing as traveling negative distance. So it has to be real. It has to be the flux has to be finite. That means that the flux cannot be infinite. You can't have an infinite scalar flux, and it has to be non-negative because you can't cover negative distance. And mathematically, the way that we could write that is that our flux has to be bounded B at all positions R and at all times T has to be greater than or equal to zero, but it cannot go to infinity. So that's what we mean when we talk about the continuity condition and the physical realizability condition. And these are conditions that can help us simplify and get closer to our solution. And it can help us eliminate certain solution forms if they would end up violating either of these conditions. Like usually when you're solving a differential equation, you recognize the form of the equation, you write the general solution, and then you find the constants that get attached to those parts of the general solution. If we have these conditions in mind, we can eliminate some of those parts of the general solution, which will just make it more simple to solve. Don't have to deal with as many constants if we can just knock some of them out if we know about these physical realizability conditions. And eventually, when we get to multi-region problems, then we'll have interface conditions. But for right now, with the bare homogeneous reactor, our boundary is just the vacuum. So in general, if we're talking about what we need to know about like a partial differential equation, these are all of the things that we want to know. We want to know about our boundary conditions. We want to know about our initial conditions. We need to know continuity and physical realizability conditions. Those are all what's going to be required to solve a problem like the one group diffusion equation. Um, this is just a quick aside on the different operators that we have talked about so far and that you've seen in your calculus class, but I just wanted to kind of spell it all out for us in case it's been a moment since we had thought about or needed to use these things. So when we were talking about Fick's law, it used the gradient of the scalar flux. So if I write gradient of the scalar flux, what that's basically saying is if I take the gradient operator, I operate on a scalar function, and what it returns is a vector. The gradient operator returns a vector. And mathematically, like if I'm in Cartesian, like XYZ coordinates, what it's saying is take the derivative of that function with respect to x multiplied by my x direction normal unit vector, take my function with respect to y, differentiate it with respect to y, and multiply that by a normal vector, and then do the same thing with my flux with respect to z. Take that flux, take the derivative with respect to z, then multiply that by my ez unit vector. And you have different forms of these operators in different coordinate systems. Um, and so that's what this is kind of showing in different coordinate systems, the form of these operators. So that's the gradient operator. The divergence operator, you can tell the difference because it has the same kind of symbol, but then there's a dot. And so it's a dot of two kind of like vector quantities. And when you dot two vectors, what kind of quantity do you get out? Vector dotted with a vector gives you a scalar. So the divergence is a scalar quantity. Whenever we were writing Gauss's divergence theorem, we were taking that net leakage, which was a number of neutrons per second, and we were rewriting it in terms of a volume integral. So it had to also be a scalar quantity when we did that conversion. And then when we plugged in Fick's law into our Gauss divergence theorem, we ended up mathematically what we would have had is this. We would have been taking the divergence of the gradient. And if you do the divergence of the gradient, by definition, that gives you the Laplacian. And the Laplacian, which is the triangle with the square, that Laplacian acts on a scalar function and it returns a scalar function. And so these are the different forms for the Laplacian in different coordinate systems. Are If I ask you something to do with Fick's law, like applying Fick's law, then depending on the coordinate system, you're going to need to know what's my gradient operator for that system. And if we're dealing with the diffusion equation where it's got the Laplacian in it, then we need to know what the Laplacian is for our different coordinate systems. This is a table that I would provide you on the exam, but I might not spell out like if I was going to give you this on the exam, I would give it to you, but I wouldn't have explanations. Like you would just basically see something like that. So it's you won't have to memorize everything, but we should be familiar enough with these operators so that if you had just this part of the table, you would be able to know which pieces correspond to which geometries. And it's kind of easy to tell in that if it's Cartesian, you only see derivatives with respect to x, y, or z. And if it's a 1D Cartesian, then the dy and the dz are kind of like infinite. So if it's an infinite medium where it's just a 1D problem, then derivatives with respect to y and with respect to z would be zero. So you in a 1D problem, you only see derivatives with respect to x. If you talk about a 1D sphere, then you only see derivatives with respect to r. Um, Spherical and cylindrical look very similar, but the main reason that they're different is that in spherical, you have these factors of r squared for like the divergence and the Laplacian, whereas in cylindrical, you only have factors of r that appear. And then 2D cylindrical is the other way. If you see a differential with r and with z, that's talking about a cylinder where you have a radial direction and you have an axial direction. So those are the different operators that we are going to need to know about and to be able to use. You'll have a lot of practice with this on the problem set 2 that I gave out, and there's copies of it up front. If you didn't grab one, they're also on our Google Drive. If you need access to that, if you don't have it already, make sure you let me know. So yeah, that's just an aside on these operators. Hopefully that's a like semi-helpful refresher if it's been a minute since we talked about or thought about these things. In general, with what we've done to get to where we're at with the one group diffusion equation, there's a lot of approximations, or well, we made an approximation to get there, and there's some assumptions that are baked into the fact that we've made these approximations. Some of these assumptions are based on just how we started the problem, like it's a uniform reactor that's surrounded by a vacuum. Um, in terms of these cross sections, we were kind of assuming that the material was homogeneous, which means that if within my medium, the cross sections aren't really changing too much. So those cross sections are like basically not very dependent on position or time. Part of our assumption was that there were no sources of neutrons, and also we're assuming part of one of the assumptions with Fick's law is that you have no absorbers. Because with Fick's law, like with the pizza box and the pizza particles going through the room, that equation and that phenomena of like gas diffusing, there's no way for that gas to be lost to absorption. So anytime that you have a problem where you've used Fick's law and your problem has a lot of absorption, your problem is going to be less accurate because absorption doesn't really happen with diffusing gases. Um, the characteristic dimensions matter in terms of how often the neutron has an interaction as it moves, like how far it goes before it interacts. This basically just means that the reactor has to be large. Your dimensions of your reactor have to be larger than the dimensions that the neutron goes between interactions. So that's why diffusion theory is much more accurate if we have a large reactor than like a teeny tiny reactor. It's one group, so we've assumed that all of the neutrons have like the same speed and average energy. Um, we kind of assume when we talked about the nuclei, the cross sections being properly averaged. Technically, with diffusion theory, we're really basically treating those nuclei as like being at rest. So it's like a cold target for those cross sections. Um, there is little to no inelastic scattering, and yeah, we're going to talk more about scattering when we get into energy dependence, but basically part of those assumptions for Fick's law is that you don't have much inelastic scattering. To the extent that there is scattering, we're assuming it's isotropic, and if all of these things are true, then Fick's law is valid, and then you're free to use one group diffusion. So those are all like the assumptions that are baked into diffusion theory, and these are just good to be aware of so that we later on in our career know when we can usefully make predictions from one group diffusion theory, and for when it might be a situation where using diffusion theory isn't so good. And there's a good example on the homework to kind of get you thinking in that I say homework, it's just problem set. It's not graded. It's just a habit. Yeah, there's a good one about the limitations of Fick's law and comparing two different cases using like an analytical solution and using the Fick's law approximation in a context where Fick's law is really bad. Um, so yeah, basically, in terms of this is kind of summarizing everything that we need for bare homogeneous reactors in one group diffusion. So I wanted us to just kind of make sure that we had everything we needed at the same in one place. So if we want to solve this one group diffusion equation, this is all of the information that we need to have. We need to know our vacuum boundary, which again just says that the flux at the external surface and at all times t is equal to 0. We need to know that initial condition, which says that our flux at all positions R at time 0 is a known shape. We know what the shape of our flux is at all positions at time 0. So phi 0 is like that initial shape. And then as time evolves from there, that shape might change. Um, Interface conditions, we actually don't have those for a one group bare reactor, but when we deal with multi-region systems, you will have interface conditions. Continuity just says that that flux has to be continuous within the reactor volume. And then physical realizability says that the flux has to be bounded from 0 to infinity. It can be equal to 0. It cannot go up to infinity for physical realizability. So this is like our good summary equation, a summary slide for one group diffusion. And I think from there, oh, I have that slide twice. Sorry. Um, that this is just reminding us how we can think about multiplication factor and the concept of criticality. Simplest way to think about multiplication factor is your production rate over your loss rate. And then based on K and the value of K, we can talk about what my multiplication factor is. If K is less than 1, it means that my losses are greater than my production. And so I have a subcritical configuration. If these are exactly balanced, then I have a critical configuration. And if my production is greater than my losses, then that's when I have a supercritical configuration. Um, when we talk about criticality, we are assuming that there's no external sources, and we're just looking at how does the population evolve in the presence of no sources. And so, yeah, what happens in our reactor is going to depend on these production and loss rates. And ideally, if we're making like a power reactor, we want to be critical. We want K equal 1 because chain reactions could go out of control if you don't have ways to have absorption. Like this is showing our fission schematic where like in the first generation, a neutron comes in, it hits an atom of like uranium-235, it makes that uranium fission into split in these two fission fragments. And out of that fission, you get two new neutrons and you get a bunch of other radiation. If both of these neutrons cause another fission, and then both of those neutrons cause two more fissions, and all of those neutrons cause two more fissions, your population increases exponentially, and then you don't have a reactor, you have a bomb. Um, Ideally, we want one of these neutrons to get absorbed into something and not make a new fission. So like get absorbed into something and just have a radiative capture, and the other neutron cause a new fission so that the number of neutrons in our population stays steady with time. Um, in terms of like thinking about that from the context of our one group diffusion equation, if we write the equation in steady form, then that d by dt term goes away. If it's steady state, then there's no time derivatives. And so this is how we could write our one group diffusion equation for steady state. And I've just moved the sigma A term onto the same side as the net leakage term, because now I've got an absorption term and I've got a net leakage term. So everything on the left-hand side is going to represent a loss rate. And then the right-hand side is my production term. So that right-hand side represents a gain rate. And if I were to take this equation and I were to multiply the left-hand side by a number such that my equation looked like this, then I could also say that that number is equal to my production rate over my loss rate, P of t over L of t. And so if that number is less than 1, then that means that the reactor is subcritical. It means that my losses are greater than my production. If they're equal, then that means my reactor is critical and my production and loss are in perfect balance. And if that number is greater than 1, it means my production is greater than my losses, and we call that supercritical. Um, and that number we know as the multiplication factor K. So if we write the one group diffusion equation with a K as that number, then we would have something that looks like this: minus D times the Laplacian of phi plus sigma A times phi equals, I would have 1 over K times my production term, times nu F sigma f times the phi. And here I've written phi just as a function of position because it's a steady state problem that no longer depends on time. And that's what we have to have when we're talking about like what this kind of equation is, which is an eigenvalue equation. In this case, k, and really this should just be k. K is what we would call the eigenvalue, and then phi is the eigenfunction. And in this eigenvalue problem, there's only one K and phi pair that satisfies our equation and our boundary conditions. Well, sorry, I take that back. There's a lot of different Ks and phis that could satisfy this equation, but there's only one of those solutions that we actually need to know about. Um, so we might be wondering about k eigenvalue problems having a time variable or a time derivative. They never do. When we talk about k eigenvalue problems, there's no time derivatives. We're looking at steady state. We're looking for k eigenvalue eigenfunction pairs in steady state. You might be wondering, can a k eigenvalue problem have sources? And generally, no. Generally, we don't include sources. We want to know about what our behavior is without sources. So we're looking at behavior without sources. We're just trying to see what does the reactor itself do, property of the materials and the geometry versus any extra sources in the system. And so technically, there are an infinite number of k eigen, I'm missing a t, infinite pairs. There's an infinite number of pairs of k and phis that could satisfy that equation, but only one of them is going to meet all of the conditions of our reactor, like matching our physical realizability. Only one eigenfunction is going to be always positive in our domain. So we're in luck because we don't actually have to solve every single k-phi pair. We only have to find the one that's positive in our domain. That special eigenfunction, we give it a name in nuclear engineering, and we call it the fundamental mode. The fundamental mode eigenfunction is the one that's positive throughout our domain, which means that it satisfies our physical realizability condition. And then that eigenfunction has a corresponding eigenvalue, and that eigenvalue happens to be the largest eigenvalue in the set. And we give that largest eigenvalue that corresponds to our special eigenfunction and name, and we call it k effective. So that's where our effective multiplication factor comes from. It's representing the largest eigenvalue that corresponds to our fundamental mode for our reactor. So this is another way to think about kind of rethinking what the multiplication factor is. And from there, we can think about the definition of K in terms of these production and loss rates as operators is kind of like the next thing to discuss. So in general, an operator is just a mathematical object that acts on a function. So we can talk about the loss operator as just being the quantities that are acting on the flux on the left-hand side of our equation. So the loss operator would be minus d times the Laplacian of phi plus sigma a times phi. And the production operator, P of phi, is an operator that acts on the flux to cause production of neutrons. And that was my new F sigma F times phi. So if I write my k eigenvalue equation in operator form, then it would look like this. This is identical to the equation, the k eigenvalue equation we just wrote in terms of operators. And that means that if I wanted to get k times phi by itself, what I would end up doing is rearranging this equation, and I would need to get like my loss and production terms on the same side, which would mean by on one side I need to multiply by the inverse of one of those operators. So the way that I could do it is to do L inverse P of phi, and that would be equal to K of phi. So this is like a more fundamental definition of the multiplication factor that you could think of if I have this operator on this eigenfunction, then this k is the eigenvalue that corresponds to this operation. And in this case, k, we could think of k effective as the largest eigenvalue of this operator, the largest eigenvalue of my L inverse P operator. And again, eigenvalue problems only deal with our system without sources. In this context, K effective is only determined and based on operators. It doesn't have anything to do with the neutron population, just has to do with the operator forms. And these operators depend on the Laplacian and these material properties. So it depends on materials and the size or the shape of our reactor and nothing else. And the only other thing that I had for today was just talking about data files. I don't know if have y'all ever used Janus before? Um, I guess I'll show y'all tomorrow how to use Janus. On one of those problems, it asks you to look up some nuclear data, and this is where we can go to find that data. Um, oh, and this was another aside. I'll also just talk about this when we come to class next time. So yeah, that's the end of our class. Thank y'all for being here. This is everything that we talked about today, kind of nicely summarized here. If y'all have questions about anything, let me know. If you need help with the problem sets, let me know. If you have questions about the lecture, let me know about that too. Thank y'all for your time. Hope y'all have a good rest of your day. Hope y'all have a good weekend. And I'll see y'all on Monday if I don't see you at office hours.